So welcome to lecture 6. As I had promised you in the last class, we are going to do some examples today. Okay? I think many of you have been looking for it. So that's today. Okay, so the first example is about the concept of Lagrangian and Eulerian and also the velocities, acceleration, or maybe I should say representation. Okay, so think of the following deformation where y1 is, first of all, recall that y is equal to y hat of x. That's an abstract way using which we have been denoting deformation, and then it has three components, right? And component wise, yi is equal to y hat I of x1, x2, x3, all three, isn't it? So think of a spatial deformation in which y1 is equal to x1 times 1 plus a square plus t square. Okay, and then y2 is same as x2, whereas y3 is equal to same as x3. Okay, a very simple example of deformation, but you will see that you can cover the concepts of Lagrangian and Eulerian representation, velocities, the acceleration form in the two different representation. So all those things can be covered here. Now let us think of what kind of what kind of deformation is this? Any idea what sort of deformation is this? So whatever is the body, you can see that in E2 and E3 directions, there is no displacement, because you see that the deformed coordinate is same as the reference in the two directions, no? E2 and E3. So it's only displacing in the x direction, right? Yeah, so it's a one-dimensional example. So from here you can also derive and also see it's a very special case. Y1 only depending on x1, but in general y1 can depend on all three, x1, x2, x3. Likewise, y2 is only depending on x2 here, and y3 only depending on x3. So it's a very special case of example. So from here you can also say that u1, the displacement related to the reference configuration, that's simply x1 into a squared t square, right? And u2 is equal to u3 is equal to 0. So now you can see that it's indeed one-dimensional displacement example. And as you increase x1, the displacement is getting proportional to x1, right? At x1 equal to 0, displacement is equal to 0. So this can be thought of as an example in which, suppose you have a beam which you have clamped at, over here. So this is E1, E2, and coming out is E3. And then you are pulling this beam, okay? But in the actual case, when you pull it, it also contracts in the lateral direction, isn't it? So when it contracts, the displacement will not be zero in the lateral direction. Okay, so obviously, so this example in that case is not really physically denoting the extension of a beam. But suppose that you are pulling it in such a way that it is also constrained in the E2 and E3 directions. Okay, and you're only pulling it in the one direction. Just think of such a scenario in which it is constrained against any displacement in E2 and E3. Okay, somebody says U1 is not right. Why do you say that? U1 is simply Y1 minus X1, right? And that should be right. Krishan? Okay, so now think of, let us talk of velocity, for example. What is the velocity? What will be acceleration? So what kind of representation is this, first of all? This is obviously Lagrangian representation, right? So what is then velocity? You can recall that velocity v is simply del y hat over del t at constant x, right? Because fixing x is same as fixing the particle. So you can now also look at component wise velocities. So that means v1 is simply going to be del y1 hat over del x1, which is just a square t square, isn't it? Sorry, I think I made some mistake here. It is del y1 hat over del t. So what you get is 2 times x1 a square into t. Okay? And obviously v2 and v3 are equal to 0, right? Because it is fixed in 2 and 3 directions. Now you see this representation, this is Lagrangian representation. So if you want to get acceleration a1, it is again simply del v1 by del t, right? At fixed x. So the fact that you already have a Lagrangian representation, it's really good. You can directly differentiate with respect to time. And what you get is 2 times x1 a square. Okay? So far it looks quite trivial, isn't it? But let us think of bringing the Eulerian representation. So v1, as you see right now, it's in terms of x1. Can we write it in terms of Eulerian coordinates? So we have to write it in terms of the current position. So for x1, we have to replace this with y1. So we can come back to this map and substitute it over here. So you can see, for example, x1 is y1 over 1 plus a square t square, right? So we put it here, and then we get v1 is equal to 2 times a square t times y1 and divided by 1 plus a square t square, isn't it? So I hope all of you will agree with this. So with this v1, can we find out what will be acceleration now? So remember, this is like V1 bar, isn't it? It's Eulerian, where this is V1 hat, this is A1 hat. So once we have V1 bar, how do we get A1 bar? So can you recall what was the formula for A bar in terms of Eulerian derivative? So it was, if you recall, it was del V bar over del T at constant y plus the gradient of velocity with respect to y, the Eulerian gradient, multiplied with velocity again, isn't it? And you can remember the significance of the two terms. First one is local acceleration, and the second one is what we say convective acceleration. So, using this representation, what is then the local part of acceleration? You have to keep y fixed and simply take the derivative with respect to time. So what you get here is, so you have time present on both numerator and denominator. First take the derivative of time in the numerator, and what you get is 2 times a square y1 over 1 plus a square t square. Okay, then for the denominator, so you have to use chain rule, and what you get is minus 2 times a square t y1 over 1 plus a square t square whole square, and then the derivative of the denominator with respect to time, which gives you 2 times a square t. Okay, so I can, so that's just the local part of acceleration. You see, it's a bit complicated now. The Eulerian derivatives were so simple, but this is just a specific example. In other examples, taking the Eulerian derivatives might be easier. Anyway, let us now look at the other part, the gradient of velocity. So by the way, remember that this is V bar, it was just E1, no? So this is all in E1 direction. If you think of in the vectorial form, it is this times E1. Okay. Now, what's going to be this gradient? So the velocity bar is 2 times a square t y1 over 1 plus a square t square e1. Okay, therefore the Eulerian gradient, you can recall the formula for the gradient. Okay, it is del v bar over del y I tensor product ei, isn't it? So now V bar has got just even component. So we can say it is just del V bar 1 over del yi into E1 tensor product EI. Correct? Because V bar is simply V1 E1. But then you see that V1 bar is only dependent on y1. It does not depend on y2 and y3 in this particular case. So this is also then equal to del v1 bar over del y1 of e1 tensor product e1, isn't it? Okay, so now we have this formula for the Eulerian gradient of velocity, and that we can put it here in the solution that we're working out. So we have Eulerian gradient, which is C del V1 bar by del Y1. Looking at the example or the formula for V1 bar, it is simply 2 times A square T divided by 1 plus A square T square of E1 tensor product E1. Okay, so we can come back here and write 2 times A square T divided by 1 plus A square T square of E1 tensor product E1, and this has to be then multiplied with the velocity itself, which is again v1 e1. Okay, so that's 2 times a squared t y1 over 1 plus a squared t square times e1. So don't make an impression that Eulerian is so bad. The the expressions are getting so big, whereas Lagrangian, you see, it was so simple. Can you see this? It was so simple. But this is just a specific example, like I told you. You can think of another example in which Eulerian will be really simple and the Lagrangian then becomes really, really bad. Okay, so what do I do next? So over here, see, you have a second order tensor multiplied with a vector. So how do we multiply a second order tensor with a vector? So that's where you have to know how that is done. And I guess I also discussed this in the last class. So if you have, for example, A tensor product B multiplied with C, okay, A tensor product B multiplied with C, then by definition, this is B dot C times A. Okay, the last one, B, has to be dotted with what you're multiplying with, and then you simply have this A remaining. Okay, and you will see that this is equivalent to, the second order tensor is like a matrix, isn't it? Whereas this vector is like a column. So this definition of multiplying second order tensor with a vector is equivalent to doing matrix times column. If you work it out in component form, it is equivalent to doing matrix times column. Okay, I hope that all of you are going through my notes, mathematics lecture, because we are going to have a quiz this week. Okay, so having seen that, you see that here we have this second order tensor which has to multiply with this vector e1. So it becomes e1 dot e1 into e1, and e1 dot e1 is 1, right? So it is then simply e1. So what you see is that the local component is also along e1 and the convective component is also along e1, which makes sense also, right, for this particular example. So let us add them all together. So we can take 1 plus a square plus t square whole square as common. Okay, so look at the first term. From here you have 2a square into 1 plus a square t square times y1. Okay, the second one is then going to be, let's see, yeah, so that's simply minus 4a to the power 4, please correct me if I'm making some mistake, into t square into y1. Okay, then the convective term, that's plus 4 times a to the power 4 t square into y1, isn't it? Yeah, I think so. So what you can see is that one part of local component is cancelling the convective acceleration here. So these two are getting cancelled. And therefore what we have finally is simply 2 times a square y1 over 1 plus a square t square. Okay, so that's the Eulerian form of acceleration. So this is basically a bar 1, a1 bar. Okay, and let us see, does it match with the Lagrangian form? So in the Lagrangian form we have simply 2x1 a square. So do you think it is matching? So indeed it is matching. So if you, in place of y1 you write it in terms of x1, then it really becomes 2 times a square x1. So this was an example in which we did some calculation and found out how to work with Lagrangian and Eulerian coordinates. Okay, any query on this problem? Any question? Of course, it has to always match because it's acceleration, no, it's the same physical quantity. Therefore, it has to always match. If it is not matching, then there is something wrong. It's the same physical quantity, right? The acceleration of a particle in Lagrangian or Eulerian form, it has to match. But you have to ensure that you are comparing the acceleration of the same particle in the two forms. If you compare acceleration of two different particles, then certainly it will not match. Yeah, there are two components, local and acceleration, local and convective, and you saw that here already. So this part is local and this part is convective. Yes, you're right. So somebody, Deep Sikha is asking, can we just substitute x1 in Lagrangian acceleration, then we get Eulerian directly? You're right. So we already had this a1 hat equal to 2 times x1 a square. So this is Lagrangian. You can directly substitute x1 in terms of y1 and you get the Eulerian representation. Here it is possible because you have an analytical formula for y1 in terms of x1. Often you don't have such an analytical formula. Then it is not directly possible, but for this particular example it is possible, and you will see that you get the same thing. Well, we usually don't have to solve for both, but this was just an illustration how we can work with both the framework. And of course, in the question or in the exams, I can ask you work it out in both the frameworks. This is for understanding purpose. Okay. So in the Lagrangian, when it is in terms of x, it is directly in terms of the particle. When it is Eulerian, it is in terms of spatial coordinate y. So that's the beauty of the two representation. In fluid mechanics, people work with Eulerian. In solid mechanics, people work with Lagrangian, mostly. Okay. So let's move to another example. So the next example is more, related to solid mechanics, I would say, which is useful for everybody. So think of, a hollow cylinder which is occupying the following region in the reference configuration. So R ref. So think of the hollow cylinder. Okay, all of you know a hollow cylinder, right? It has inner radius, outer radius, and it has some length. So in the reference configuration, the region occupied by this is given by this mathematical representation. So I'll say it's all the coordinates x1, x2, x3 such that a less than x1 square plus x2 square to the power half less than b comma 0 less than x3 less than l. See, this is a mathematical way to write this and say that the inner and outer radius are a and b and the length is l. Okay, if I have to draw this, then if it is E1, E2, then here is the cross section of the cylinder. Okay, and then well, let's make this E1 and this as E2, so that both inside is your E3, and then the cylinder is along this E3 direction. Okay, of length L. So what it says is that these components x1, x2, x3 are obviously with respect to E1, E2, E3. Okay, as shown in the picture. And then it says the deformation of the cylinder is happening according to the following formula. So y1 is equal to fr times x1 into cos of phi x3 minus x2 into sine of phi x3. Okay, then y2 is equal to fr into x2 into cos of phi of x3 plus x1 into sine of phi of x3. Okay, and y3 is equal to lambda times x3. So here this r is of course denoting the radial coordinate, okay, which is such that r square is equal to x1 square plus x2 square. So in the cylindrical coordinate, that's the r. Okay, and phi of x3 is just some function. Okay, it's a function which only depends on x3, and lambda greater than 0 is a constant. Okay, so with this mathematical formula, can you think of what physics is this denoting? What kind of deformation is this denoting? Anyone? Just think about this. Yeah, it is Lagrangian because it is in terms of x. But then, I mean, what sort of deformation is this? Physically, what is happening to the cylinder? So, Pawan, okay, so all of you are saying it is twisting. I mean, some of you have said it. But let us see. So, you are right that it is corresponding to twisting. But let's really see why we say that. So, well, it is not just twisting. If you see it carefully, is it just twisting or there is something more? And elongation. Very good. That's true. For example, you see the length of the cylinder. What happens to the length of the cylinder? So you see that y3 is lambda times x3. So length changes to lambda L. Originally it was L, then it is changing to lambda L. So if lambda is greater than 1, then it is elongation. And if lambda is less than 1, then it is compression. Okay, so the length is also changing. What else is happening? So let us try to see it more carefully. So if we do y1 square plus y2 square, then what do we get? Um, so it is simply f square into x1 square plus x2 square. Can you see this? So y1 square plus y2 square is f square into x1 square plus x2 square. So when you work out, no, this is what you will get. But x1 square plus x2 square is simply little r square. So this is same as f of r whole square into little r square. Okay. And what is y1 square plus y2 square? So that's like the, the cylindrical radial coordinate once the body has deformed, isn't it? So suppose I denote that by RD. So RD square, that's equal to F square into R square, D for deformed. So that means small r is F into R. So can you see what is happening to the radius of the cylinder? The original radius small r, so RD, is getting multiplied with this function F, isn't it? So whatever is the original radial coordinate, that's getting multiplied with this function f, and you get the final deformed coordinate. Then does it mean that it is simple inflation of the tube? Is the tube just inflating? That means just the radial coordinate is changing. So you see here you found that it is not just twisting, there is also some inflation occurring. So the radial coordinates are also changing. In case of twisting, it is the radial coordinates usually do not change. That's our picture of twisting from undergraduate course. So here the radial coordinate has changed. Now if we think of the theta coordinate, then what's the theta coordinate? So in the deformed configuration, the theta, what will be tan theta deformed? Isn't that y2 by y1? If y2 and y1 are the coordinates, then the deformed is simply y2 by y1. Tan theta d is y2 by y1. Now let us work it out and see what is it coming out to be. So okay, that's doesn't look so easy. So this is x2 cos phi x3 plus x1 sin phi x3 divided by x1 cos phi minus x2 sin phi. Okay, let us try to write this in terms of everything in terms of cylindrical coordinates. So x2, x1, let us write this in terms of r and theta, the original cylindrical coordinate. So x2 is then r sine theta, isn't it? All of you know if x1, x2, x3 are Cartesian coordinate. So x1, x2, x3 Cartesian coordinate, and I want to go to r theta z, then x1 is equal to r cos theta, right? x2 is equal to r sine theta, and x3 is simply z. Okay, so let us substitute that here, and what we get is, you see this radius r will cancel from the both because it is there in both numerator and denominator. So what we have is then sine theta cos phi plus cos theta sin phi divided by cos theta cos phi minus sin theta sin phi. And now you can see the numerator is sine of theta plus phi and denominator is cos of theta plus phi. Okay, so that's tan of theta plus phi, right? So what you see is that theta d, that in the deformed configuration, the theta coordinate is simply theta plus phi, where this phi is a function of x3, right? So can you now see that this is also leading to twisting? You see the theta coordinate is changing, but it is not the same for every x3. As you move along the length of the tube, phi is changing, and that's what happens in case of twisting, isn't it? In case of twisting, the theta, the rotation of the cross section is different at different length. So if I come back to this picture, then a point originally over here will, it's going to move. So it is right now at theta equal to 0, but then it's going to move to this phi. Okay, and also the radial coordinate is also going to change. So right now it is small r, but then it has to change to r times f. So this point originally is small r 0 comma 0 in this case, but this has, it is moving to, it has moved here and changed to small r into f comma phi of 0 comma 0, isn't it? So you see a point is moving radially as well as in the circumferential direction and also in the z direction. So all the movements are happening here, but it is in such a way that for a given cross section, because you see this phi is only depending on x3, it does not depend on x1 and x2. So for a given cross section, say I look at this cross section over here, so if you look at this cross section, then the entire cross section as a whole is rotating by phi, that angle phi. Every point of this cross section is rotating by that angle phi. Okay, And every circumferential line, if you think of any line having same radial coordinate, so this is a circular line, a concentric line, all having the same radial coordinate. So all points on this line move outward by the same distance. So the radial coordinate of all these points, which are originally the same, is finally also the same. So that's what happens in case of twisting. So, I mean, the trademark for twisting is that every point in the cross section moves by the same angle. Okay, and it is different for different cross section. So the cross section over here at x3 equal to 0 is moving by phi of 0, whereas this cross section is rotating by phi of x3. Okay, so can someone tell me how much is the twist? How much is the twist in this beam? Anybody? Are you guys there? How much is the twist? Phi of L. So that's the total rotation. That's the end-to-end rotation. So end-to-end rotation here is end-to-end rotation. That's phi of L minus phi of 0. But I'm asking the twist. Twist is not end-to-end rotation. How much is end-to-end rotation? Sorry, how much is twist? Anybody? No one? Divided by L. Well, that's if the twist is uniform, no? But here we don't know this function phi. How is this function phi changing with x3? Is this linear in x3? We don't know. So what do you think? How much is the twist? Anyone? L into phi of x3 by small r. Well, that's a very interesting formula, but it is not true. First of all, what is the dimension of twist? It is angle by length. So it is length inverse. So when you have uniform twist in a beam, then the twist is end-to-end rotation divided by length of the beam. But here this phi of x3 is not changing, it's not linear. So Rahman says summation of angle at all sections. Well, what does that mean? Integrating phi with respect to x3 and then dividing by L. Why do you want to integrate phi with respect to x3? Phi itself is the angle. What will you get after integrating it? Phi itself is the angle. Okay, so Kalpesh has gotten quite close. He says phi of x3 minus phi of 0 divided by x3. But what is this giving you? This is like an average twist in the segment from 0 to x3. In the segment of the cylinder from 0 to x3, that is kind of giving you an average twist. But I'm not talking of average twist. Just tell me what is a twist. So as of now, I think all of you have just learned about uniform twist, the problem of uniform twist. This is not the example of uniform twist. That means the twist is varying from one point to the other point. Okay, Meenal says d phi. So d phi over dx, exactly. So it is phi prime. So phi prime is so what is phi prime? It is the rate of change of angle with respect to x3. So isn't that the twist? So you have to think of two close cross sections and find out how the angle between them have relatively changed and divide by the length, divide by the distance between the two cross sections. So so twist, if I denote by kappa, the twist at x3 will be phi of x3 plus delta minus phi of x3 divided by delta, and then you take the limit delta going to 0. So this will give you local value of twist, which is simply phi prime of x3. Okay, so this is an example in which you don't have uniform twist. So depending on this derivative, if the derivative is changing, you will have non-uniform twist. If the derivative is fixed, then you have the example of uniform twist. Okay, so that's your twist. Any question on this? Okay, I'm going to stop the class here, but I'm here. You can ask me questions. So what is the answer if asked for twist from x0 to x3? Well, that's your cooked up question. What is the meaning of twist from x0 to x3? If you are asking for average twist between the segment from 0 to 3, if that is what you're asking, then you know the answer, right? Phi of x3 minus phi of 0 divided by x3. In example 1, what is u? So we had u1, no? u1 is the displacement, right? We are denoting displacement by u. So how to recognize that the set of equations given is for twist and elongation? So it's a very interesting question. Um, so I think now you can recognize, right? If somebody gives you this formula, then you would be able to recognize that it is indeed twist. So if you look at it for the first time, you won't be able to recognize. But once you have worked it out and then you see it, then suddenly you can recognize. See, the extension is a bit easier because you see here that y3 is equal to lambda x3. So you can, if you're careful and if you start visualizing what sort of deformation is this, then you can see that okay, the length has changed, so there's some extension happening. Then to see that it is twist, that's not trivial. You have to work in cylindrical coordinate and then see that okay, indeed the theta coordinate of the points have moved by the this formula that we worked out. This, so from here we see that twisting is happening. So to see that there is some twist, you have to work out the change in angle, the theta coordinate. Because that will denote the rotation, no, about the axis of the tube. And as phi is a function of x3, that means the rotation is different for different cross sections. And that's what happens in case of twisting. So somebody is asking to explain the formula for twist. See, twist, what is the definition of twist? So only then you can then say, okay, this is the formula. So in our undergraduate class, we have done torsion of beams. So there the beam was undergoing uniform torsion. So you would say that twist is simply end-to-end rotation divided by length of the beam. Isn't it, Rajvardhan? But here, the twist is not uniform, so we cannot use that formula, that end-to-end rotation divided by length of the beam. So here the twist is varying from one point to the other. So what we have to think of, so here is the cylinder. If you want to know what is a twist over here at this point, so think of cross section at this point, two neighboring cross section at this point, and find out end-to-end rotation between these two cross sections. Divide by the length between the two cross sections and bring the two cross sections close to each other by taking this delta go to 0. So that is what we have done here. Do you remember the same thing happens even with elongation of a beam? So if you have a beam which you are elongating, so suppose u is a function of x here. So this is the x coordinate and u is a function of x. So how much is the strain? How much is the longitudinal strain? Epsilon. So somebody would say, okay, it is simply u of L divided by L. But that's the global longitudinal strain. That's kind of average longitudinal strain. What if u is not linear? So that in that case, if u is not linear, if u is some crazy function, then the longitudinal strain varies from point to point. Okay, and then your epsilon is u prime du by dx. So what you have to do is you have to think of to close a very infinitesimal segment of the beam and find out change in length of this segment divided by its original length, and that will give you this u prime. For example, think of this segment. This point is at x and the other one is at x plus delta x. So how much is the final length? So final length would be, so original length of course is delta x. The final length is what? X plus delta x plus u of x plus delta x minus x minus u of x. That's the final length. So how much is the strain then? So let me say here, this is the original length and that's the final length. So strain is then change in length, right? Delta L divided by original length. So delta L is then, so you can see here these two are crossing. So you have delta x plus u of x plus delta x minus u of x minus original length is delta x divided by the original length is delta x. So these two also cancel, and so you have u of x plus delta x minus u of x divided by delta x, and then you have to take the limit delta x going to 0 because you want to get the local value of longitudinal strain, and this gives you u prime. Okay, the similar analogy is also occurring for twist here. So I hope you got the answer. Yeah. So somebody says in lecture 4 we derived for a hat which we are using for E minus in the first example. So I'm unable to understand what is the meaning of E dash. You mean acceleration? That's true. So we had derived that formula earlier, the formula for acceleration, and that we have used here. So these are the Lagrangian form, and this is the Eulerian form. Quiz time syllabus. So syllabus, it is from lecture 1 to 6 of AML 841, and time I'll let you know. It's going to be on Saturday or Sunday. Okay, I'll let you know.